Class, this is 8.1, 8.2 notes. So let's take a look and see if we understand what's going on with this. So the first part of, if you read 8.1, it's really like half a page long. It's really not much. It talks about the three different types of bonding. Those three different types of bonding, of course, are for chemical bonds. They are ionic bonding, covalent bonding, and metallic bonding. Metallic bonding is when metals and metals, obviously atoms of metals, are joined together using their sea of electrons as a way to bond. So let's continue on with ionic bonding and see what's going on. So as you notice here, energies of ionic bonding. So one of the things that we've talked about is ionization energy. So what is ionization energy? Ionization energy is when sodium in its gaseous form here, not a plus, goes to sodium with a +1, +1 electron like that. And that energy that's associated with that is 495 kilojoules per mole. So that means for 1 mole of sodium to go from 0 to a charge of 0 to +1, and that 1 electron then is available, that's 495 kilojoules per mole. So what else is going on there with sodium when we have also chlorine, and chlorine is then, as a gaseous here, is accepting 1 electron like this and ends up as Cl with a -1. So notice that we have a certain amount of energy that is being absorbed. So it costs sodium more to give up an electron than it does for chlorine to give off the energy to take in an electron, but not by much, actually. It's actually pretty close as far as energy is concerned. So as far as the ionic bonding goes, these numbers don't explain why the reaction sodium metal and chlorine gas form sodium chloride is so exothermic. So you have this happening all over the place. You have chlorine gas, then you have sodium, and then how does it get together? So let's talk more about so there must be obviously a third piece of the puzzle. What is yet unaccounted for is the electrostatic attraction between the newly formed sodium cation and chlorine anion. So once the sodium gives up the electron and chlorine takes in the electron, that's when you have this part right here where are we at here? The sodium ion is the top one. The chlorine ion is the bottom one. Sodium's positive, chlorine's negative, and because they attract each other, that's where the extra energy is coming from. Okay, that's what we're talking about here. It says what is yet unaccounted for, the electrostatic attraction between the positive and the negative. Okay, so that ends up being something called lattice energy. Lattice energy is the energy required to completely separate a mole of solid ionic compound into its gaseous ions. So the stronger the attraction between the two, the larger the lattice energy. The energy associated with electrostatic interactions is governed by Coulomb's law. And this is the Coulombic charge of the first, the Coulombic charge of the second, and then, of course, divided by the distance. And then there is, of course, some type of, as always, some type of constant that's associated with this. Okay? So lattice energy then increases with the charge of the ions. It also increases with the decreasing size of the ions. So when you have something like lithium fluoride and you have those two attached to each other, notice how large the lattice energy is. That means it's more difficult to pull them away from each other. It takes more energy to break them apart. But it also means that if you have higher charges, that also increases the number or the amount of energy it takes to rip the positive and negative parts away from each other. So lattice energy is the key. Take a look at the energy that it takes. So we're going to start off with just sodium and chlorine. Actually, where are we going to start off? We're going to start off with sodium metal and chlorine gas here. And then we have to change the sodium to gas. That's what happens here. And then instead of being Cl2, 1/2 Cl2, we have to change the Cl2 to just regular chlorine atoms, which means breaking the bond between Brinkelhoff for chlorine. So just then, so these, when we're going up, we're expending energy. We're putting energy into the system. And then we do our first ionization energy for sodium here. That's what this is. This would be the 495 kilojoules per mole that we talked about before. That gets us to sodium with a plus 1 charge and 1 electron, and then chlorine gas. And then we have the electron affinity for chlorine, which combines these two and puts us down here. So when we go down, we're giving off energy. So notice we climb up, up, and up until we get to the electron affinity, which gives off energy. And then here's where the lattice energy drops all the way down. So lattice energy is a huge, huge part of this. Okay, huge part of why there's so much energy given off when you put sodium and chlorine together. Okay, so that's about it for lattice energy. Next coming up then is going to be, this talks about stuff that we've already talked about. For ionic bonding, this is already talking about, when you see the blue line here, the blue line means that we're dipping into core electrons, which means that we're ripping out electrons of electrons of noble gases. That's what core electron is referring to. Electrons from noble gases, and that happens at a much greater energy cost than it does if we're just ripping off valence electrons. So for instance, they tend to stop losing electrons once they attain a noble gas configuration, which is true for just about every, there we go. There's the 3 bonds, so this is almost like in the beginning part. So now we just talked about ionic bonds, electrostatic attraction between the atoms called lattice energy, and then we're going to get into covalent bonds, and that's the next one for 8.3, 8.4.